Hi everyone, this is the solution video for the in-class activity we did for respiration and the oxyhemoglobin curves. Okay, and so here is the graph that we're looking at to understand oxyhemoglobin curves. And what this does is it's a dissociation curve. It explains to us how pressure or partial pressure of oxygen in the blood is related to how saturated the hemoglobin can be, meaning how much oxygen it can carry. And then we can also use this curve to predict how much oxygen gets released to the tissues. So let's first orient ourselves on this graph. So you can see on the x-axis, this is the partial pressure of oxygen of the blood in millimeters of mercury. So this is the partial pressure that oxygen exerts within the blood, and the units is millimeters of mercury. Okay, you want to keep that in mind because we want to make sure that we write our units correctly. Here you can see at 100 millimeters of mercury, this graph is actually just telling us, this won't be on every graph, but it's telling us that at 100 millimeters of mercury, that's the normal partial pressure of oxygen. It says here at the pulmonary capillaries. So remember, pulmonary capillaries are the capillaries that are at the lungs surrounding the alveoli. And so oxygen is diffusing into the capillaries there. We're loading the blood with with oxygen, okay, and it's binding onto the hemoglobin within the red blood cells. So this picture also is showing us that this is a fully oxygenated or fully saturated hemoglobin molecule, okay, or within the blood cell too. That's what the key is telling us as well. Okay. At 40 millimeters of mercury, this graph is telling us that that's the average resting partial pressure of oxygen in the systemic capillaries. So remember, in the systemic system, once our blood leaves our arteries and arterioles, it goes into the capillaries that surround our organs. These are the cells that are doing work, okay, the cells within the organs. So they're using oxygen. So that means we've released oxygen to those tissues. So the partial pressure of oxygen in the blood is lowered because there's less oxygen in there. It went into the tissues. Okay, and this picture is showing us just a stylized view of a partially saturated hemoglobin molecule. Again, the hemoglobin being inside of the red blood cells. Okay. So basically, here are some things to remember is in the arteries or at the arterial end of the capillaries, okay, or around the lungs, the partial pressure of oxygen is high at 100 millimeters of mercury. Okay. At our tissues, where tissues are using oxygen, okay, so at our tissues or in the venules or on the venous side of the capillaries there, at rest, the partial pressure of oxygen is 40. Okay, so what we're going to do is use this curve to see, well, how much oxygen was released or what percentage was released. One other thing I want to mention is this is kind of a sigmoid curve here, and then it flattens out. Okay, you have a plateau. So you can see that at 100, we're almost fully oxygenated. Okay, your blood is never completely 100% oxygenated, although we might just say that because it's like 99, 98. That's normal. Okay. So it's okay to tell me that blood is fully oxygenated at 100%. I will take that. But just realize it's never fully 100%. But you can see if we continued with higher pressures here, you would see that we couldn't really load any more oxygen into our blood. At 100, it's pretty fully oxygenated. So if you were breathing pure oxygen, say at 600 millimeters of mercury, you really wouldn't be oxygenating your blood anymore. Okay. But why do we do that? Why do we give people oxygen? They are in a disease state or in some kind of stressed state where they're not fully oxygenating their blood. So for whatever reason that is, we're giving them more oxygen to be able to do that. COVID was an example of that. What if you're a hiker climbing Mount Everest? Guess you're more than a hiker, you're a climber. Okay? At Mount Everest, the atmospheric pressure is so much lower that the partial pressure gradient of oxygen between the atmosphere and the inside of your lungs is much smaller. Okay, because the atmospheric pressure is lower, so you don't have as much of a gradient, so it's harder to get oxygen into your blood, so you might breathe supplemental oxygen at that point, right? So again, this is under normal conditions. Okay, the y-axis over here on the right side tells us the volume percent of oxygen in the blood. We're not going to use this too much, but I just suffices to say that what this is telling us, it's the volume percentage of oxygen in the blood, meaning the milliliters of oxygen bound with hemoglobin per 100 milliliters of blood. So again, don't worry too much about that, but what you are seeing on the red side here in the arteries, that volume is much higher than it is in the blue areas. This is the venous area. Okay, that volume would be much lower according to the curve, because again, tissues are using oxygen. So the blood we bring to the tissues is high in oxygen. The blood we carry away from the tissues is low because the tissues use some oxygen. We're going to just focus on this y-axis on the left side here. On the left side here is the percentage hemoglobin saturation. So again, what percent saturation is occurring in a hemoglobin molecule? So one hemoglobin molecule combined up to 4 oxygens. Okay, but we have 250 million hemoglobin molecules in one red blood cell. So we technically fully saturated at 100% would be like a billion molecules of oxygen, but we don't want to deal in billions, so we're just looking at percentages. So here you can see is that after we go to the tissues, if hemoglobin released 3/4 of its oxygen molecules, well, this is only a quarter saturated, right? So saturated is what's left. Okay, here, this is showing you that every binding site of oxygen is full in the hemoglobin, so this is fully saturated. And that's given you here on this key. So whenever you're looking at a new graph, if there's a key, make sure you read it. Make sure you read the axes so that you understand what this graph is indicating. So normally when we look at oxyhemoglobin curves, you won't see this dotted line. Again, this was just extra information they're giving you, but you will see this curve. And on here it's red. You'll get this y-axis and this x-axis. We don't worry about this x-axis, okay? So let's look at the questions. What is the partial pressure of oxygen at the arteries under normal conditions? So I put this here. This graph shows you, but I want you to memorize this. This is something I want you to just remember. So at normal conditions, this tells us here, it's at 100 millimeters of mercury. So just remember that, okay? 100 millimeters of mercury is the partial pressure of oxygen when our blood gets fully oxygenated. So that's at the arteries, that's at the pulmonary capillaries, okay? That's at the arterioles, and then that's what's entering the capillaries at the tissues. But now there are some questions just to get you to practice to read this graph. At a partial pressure of oxygen of 90 millimeters of mercury, what percentage of the binding sites on hemoglobin is occupied by oxygen? Okay, another way of asking that question is, what is the percent hemoglobin saturation? Okay, so that's what this graph is telling us. When I ask what is the percent hemoglobin saturation, what I'm asking is what percentage of the binding sites on hemoglobin are occupied by oxygen. Again, so this is going to tell us, it asks us to look at a pressure of 90 millimeters of mercury. So we look here, and then all you do is you just have a line straight up till you hit the red line. Now you look over to the left and you estimate what that's falling on. It's about 97, 95%. Not much different than when it's 100 millimeters of mercury. Okay, so here, the question is, what percentage? So my answer is 90, we'll say 97%. Don't forget percent. The answer is not a pressure. Don't put millimeters of mercury, because I asked you what is the percent. I'm emphasizing this because it's a common mistake on the test. Okay, got to get your units correct. All right, so that tells you even when the pressure falls slightly, our hemoglobin still hangs on to that oxygen. All right. B, at a partial pressure of 25 millimeters of mercury, what is the percent hemoglobin saturation? Okay, so now we're looking down here. Okay, I'm in between 20 and 30. I'm going to go up till I hit the red line. I hit it right about there. To me, that looks like about 45%. Okay, so at a partial pressure of 25, then the percent hemoglobin saturation is about 45. Okay, so what did that just tell me? When the partial pressure of oxygen goes down in the surrounding tissues or in the blood, hemoglobin will release its oxygen. Okay, it didn't release all of it because we're down to 25%. All right, so that's important to know. So that could happen when your tissues are more active because they're pulling more oxygen out. In the local area, that partial pressure of oxygen could go lower. Well, we need to release more oxygen because the tissues, if they're working harder, they need more oxygen. Okay? All right. Now we're going to get a little more complex. Okay? Because we're going to use the information we get from the graph to answer a different question. So now it's saying if a fully loaded hemoglobin molecule reached a tissue that had a partial pressure of 40 millimeters of mercury, what percentage of the oxygen would be released? Okay, so this is not going to be answered directly off the graph. Okay, so first thing to remember, it says if a fully loaded hemoglobin molecule reached a tissue. So we're starting with 100% saturated hemoglobin. Okay, 100% saturation. Now it gets to 40 millimeters of mercury. Now it's asking what would be released. So what we need to do is what is the percent saturation at 40? Okay, so we look at 40. We go up to our line. To me, that looks like 75%. Okay, so we went from a hemoglobin molecule that was 100% fully saturated to the tissue where the pressure is at 40. So now it's 75% saturated. But the question is, how much was released? So if I started with 100% saturated and I ended with 75% saturated, you subtract 75 from 100 because 25 was released. Okay? 25 was released. Rewind that if you need to hear that again. Okay. The other number I mentioned to remember, I said when we're fully loaded, the partial pressure is at 100 millimeters of mercury. Well, at rest, when the body is just at rest, you're not doing anything in particular strenuous. At the veins or at the venule end of our tissues or in the veins or the blood heading into the lungs, that partial pressure is at 40. I want you to remember that. Okay, so I might ask you, what is the partial pressure of oxygen in the veins? 40 millimeters of mercury. Okay. All right, we're going to do some more of these. Here now is the same, the solid line is the same curve as above. This is under normal conditions. And what we're going to see now is that our oxyhemoglobin curve shifts when when other conditions arise. And so in this case, it shifts when our pH changes. So recall that normal blood pH is about 7.35 to 7.45. We're slightly basic in our blood. So if that shifts below 7.35, we're considered our blood is acidic. And it depends on how far down it goes, the pH scale, how acidic it gets. So this is just an example showing you that the relationship between hemoglobin and oxygen actually changes when our blood environment gets more acidic. So here's an example of 7.2. Okay, so now we're going to see that more oxygen actually gets released when our blood gets and our tissues get a little more acidic. Okay, and so we'll explain why in these questions. So first, let's go. What percent of the hemoglobin sites is bound by oxygen at a partial pressure of 40 millimeters of mercury and a pH of 7.4? So this question is the same as the curve above, okay, that we did up here, but I recreated it here because it's telling you to look at 40 millimeters of mercury there, and I want to know what is the percent hemoglobin, or what is the hemoglobin saturation when the pH is 7.4. So it's telling you this curve indicates what it is when it's at 7.4. So I'm going to go from 40, I'm going to keep going up until I hit the solid black line, and that should be about 75%. Okay, 75% you write here, because I asked for a percentage. Then it says, what percentage of the hemoglobin sites are bound by oxygen at a partial pressure of 40 at a pH of 7.2? So now I'm going to the 40 partial pressure, and I'm going up until I hit the red line. And at the red line, that looks like about 50% to me. Okay, 50%. So what happened was, when the environment got more acidic, even if the partial pressure of oxygen didn't change, the hemoglobin released more oxygen. Okay, so the question is, what is the metabolic reason for this change? Okay, so relate this back to cellular respiration. If metabolism increases, that means your cells are working harder. So in this area, wherever we're at in our body, that organ is working. Okay, when an organ is working, cells need to make more ATP. Okay, we realize that when cells make more ATP, they're releasing more carbon dioxide. When carbon dioxide mixes with water, it produces an acid. Things get acidic. It's the reason why we got to get rid of carbon dioxide. Okay, so this organ is working harder. It's releasing more CO2, and the local area is becoming more acidic. So now relate what's happening to hemoglobin, which is a protein in this acidic environment. This is general bio. You learned in the concept of enzymes, which are also proteins. So this is true of all proteins. When proteins like enzymes get into a more acidic environment, they start to unravel. And if they denature, that means they've totally unraveled their shape and they're not good anymore. But this is just a slightly acidic environment. So what's happening is that the protein molecules are starting to release their bonds, but in doing that, it doesn't bind to oxygen as tightly, and it releases oxygen. Okay? So I found this on the web. Sorry, Siri keeps answering me. So again, what is the metabolic reason for this change? We know the tissues are getting more active because they're producing more CO2, which is making the environment acidic. The acidity is what's telling us that. Okay, when the environment's more acidic, hemoglobin starts to release its bonds, and it releases more oxygen. We saw that it went from 75% saturated to 50. So it released 25% more, 25% oxygen to the tissues in an acidic environment. And again, when cellular respiration is occurring, we need oxygen to drive cellular respiration. So this is actually releasing more oxygen. So this is a local situation, right? Over time, if this continues and the blood starts to, as a whole, get more acidic, then we're going to have different homeostatic control systems. The hypothalamus is going to detect it. Okay, but this is just a local situation at the tissues that locally our tissues are working harder, because when they work harder, the environment gets more acidic, but because CO2 gets released, we actually are able to get more oxygen to accommodate the harder working organ. Okay, that's the metabolic reason. Similar to acidity is temperature. Here's temperature. Our normal temperature is 37 degrees Celsius, which is 98.6 degrees Fahrenheit. So this is the same curve we saw above. This is normal conditions. Temperature can shift when our bodies are working harder. What happens when you work out? Your skeletal muscles are making more ATP. When we're making ATP, what we're doing is we're converting one form of energy to another. We're converting glucose to ATP. General Bio told us in thermodynamics, law of thermodynamics, when we convert one form of energy to another, we lose some of that energy as heat. So your body temperature is going to rise. That changes the curve, similar to what it did with acidity. So remember, proteins denature when temperature gets higher. So again, hemoglobin isn't totally denaturing, but it's loosening up the beginnings of it, and it releases oxygen. Okay, so let's go to the questions. What percent of oxygen is unloaded to the tissues that have a partial pressure of 40 millimeters of mercury at 37 degrees? Okay, look at this question though. It is different than this one. This one is asking the percent saturation. You can read that directly off the graph. This one is asking how much is unloaded at the tissues, but we first have to find out the saturation. So remember, blood heading to the tissues are fully saturated at 100%. Once they reach the tissues, and we know that's happening because we're mentioning 40 millimeters of mercury, so we're going to look there. We're going to go to our solid black line curve, because that's the 37 degrees. 37 degrees. Okay. And when we do that, we're at about 75% saturation. But the question is, what was unloaded? So if we started with 100% saturation and we got to the tissues and now we're 75% saturated, 100 minus 75 is 25% was unloaded or released. That's this answer. Now it says, what percent of oxygen is unloaded to the tissues that have a partial pressure of 40 millimeters of mercury at 43 degrees, so at the higher temperature? So we're going to go to the line at the dotted line. So I go to 40 millimeters of mercury here. I go up to there. That looks like, I'm going to say 55%. Okay. So now I went from 100% saturated to 55% saturated. So we released 45%, because that's the question. How much is unloaded or released? We unloaded 45% when the temperature went up. What's the metabolic reason? Again, with metabolism, we're making more ATP. When we make ATP, cellular respiration releases some of that energy as heat. That raises the temperature in the local area. Heat causes proteins to start to unravel. This isn't a total denature, but it's starting to, enough to pop the oxygen molecules off. The tissues benefit because we just said they're working harder, and we know that because there's a higher temperature, so they need more oxygen. Again, a local control. If this continues, then your body as a whole gets too hot. The hypothalamus gets the signal, and you start to regulate the whole temperature, right? Homeostatically, maybe you start sweating. But that's not pertinent to this question. Okay? So please review this. Review this video again if you need to. I hope this helps you understand oxyhemoglobin curves.